Yes, it's working. And I will start to share my screen. Just a minute. Okay. So let's start our class today, okay? And today we have to discuss about soil formation and how some soil formation factors are affected when we change the soil properties from a modern soil to a paleo soil, okay? I believe that everybody here know the idea, the thesis that soil is formed by the interaction between soil formation factors and sorry, sorry, and the soil formation factors are climate, vegetation, and animals acting as organisms, the parent material, and relief. And all these soil formation factors are linked by time. And time is a key soil formation factor to us because we are discussing about paleosols. Okay, so the interaction of different climate conditions like higher or lower temperatures, the precipitation, the annual precipitation, the distribution of the rain, the temperature, if you have dominance of higher temperatures or higher than 18 or 20 Celsius degree or below 0 Celsius degree, it influences a lot on the some of the soil process, and they influence also the interaction of organisms. Vegetation cover and the bioturbation formed by animals, they are very, very influenced by climate conditions. So if you has higher temperatures and higher precipitation, you induce the vegetation to be covered by, to be composed by plants that compose a rainforest or maybe a savanna. Okay, so you change from vegetation that's higher, it's dense, it's produce a lot of organic matter, and it's completely different from another kind of vegetation, a composition that's composed from direct forests, for example, or even vegetations that it's less complex, like tundra and another kinds of vegetation that cover deserts and some arid areas. So the climate conditions, it defines how organisms act and produce soil. So it's why we can understand that some paleosols are formed by different climate conditions, okay? And we can understand very easily how parent material is quite important to soil formation, because these are the materials that will be wafered and leached and mixed by animals and by climate. So parent material could be rocks, could be sediments, could be organic matter, and any kind of material, these three, that could be wafered, leached, and mixed by soil formation factors, soil process, will be the parent material of soil, okay? And of course, we can understand very easily that when you form a paleosol, sometimes you change the parent material of a soil, or you add another parent material, or even you can change the parent material properties because you increase or decrease the content of some elements, and you can increase or decrease the bulk density and some properties that we will discuss in our class. Okay? And relief, it's quite important too, because relief, it is quite related to the sea level. So if you change the sea level because you change some tectonic condition, or you change the climate condition, you change how material will be eroded and how material will be leached. If you has higher gravity potential, you will be more the material, the landscape will be favored to be eroded, like the particles, the solid particles could be more easily eroded from higher areas to lowlands. So from the highlands to the lowlands, and also the leaching of these materials. You also influence the formation of the tidal water and the presence or the absence and the position of the tidal water. It's quite important to some reduction process that influence a lot the properties of the soil. And some paleosols, they are influenced by tidal water too. So it's quite important to understand how relief influence the formation from modern soil and also influence the formation of a paleosol. Okay? Today, we will discuss how parent material influences soil formation and how parent material could be changed, could be mixed by the formation from a soil to a paleosol. Okay?
Peter, can you explain more about the with how the parent material can be different in different material parent material in paleosol. I bec- I could be different parent material in paleosol.
Yes, yes. It's quite easily to think, and we will discuss in our class today, okay, how you can change the parent material, the same parent material, or you can add a new parent material,
Mm-hmm.
okay? But we will discuss in the next
Okay.
slides, okay? Okay. Um, so these are some pictures of different parent materials. It's just too important because we need to highlight that rocks are not the same, are not equal to parent material in all cases. So we can find some soils that are formed by rocks, like this one. So the weathering of these rocks, this granite, forms this soil, this dark soil, okay? And we can understand that this soil probably will be, will have a lot of similarity with these rocks. So some properties will be very close from these rocks, from this material, because soil is very thin, it's not so evaluated, so probably a lot of properties could be very similar from these rocks. Probably this soil will be eutrophic, will be a lot of high activity clays and several other properties that remember that it's quite close to this rock, okay? And if I change from a granite to a sandstone to another rock, this soil will be very different from this one, because the sandstone will be very rich in sand content, so probably the soil will be sandy and present a low content of high activity clay and maybe a low content of clay, okay? And we can see very easily the differences between soils according to its parent material if they are low developed, they are incipient soils, okay? So some regosols, leptosols, camby soils, insect soils, they are very close to their parent material, okay? And some well-developed soils, like ferrosols or oxysols, they also are very close to the parent material, but it's not so easy to identify these differences. So we can see oxysols or ferrosols that are developed from sandstones are very different from those that are derived from undead iron formation. The color are quite different. Some of them are very yellow, like yellow color, very highlighted, and the other one are redder. So we can see a difference of colors very easily, but the morphology, the structure, the consistency, and maybe even the texture could be very similar. So some of the properties will be highlight this difference, and some of the properties could be so blurred by some soil formation factors in the case of well-developed soils, okay? In the case of parent materials, it's not so easy to identify the relation between the parent material and the soil formation factors, because sometimes you spend a lot of time that the soil was formed in very different conditions, and the leaching and the weathering will act a lot, so we can't see so easily this relation between the parent material and the soil, the paleosoil properties. But if you know how to look this relation, you can find. It's just a case of know how to should we use, how to or how to ask the soil which parent material format that soil, okay? This second picture is just to remember that we have very soils, very fixed soils formed by sediments, and can be alluvium or colluvium sediments. We can find a lot of fixed soils in marine terraces and riverbeds and another kind of materials that formed soil from sediments, okay? And the sediments can be organic or inorganic. So we can find some dark layers here that could be very rich in carbon content, in organic carbon content, and we have some yellow and red layers that probably are poor in carbon rich or carbon poor layers, okay? So we should understand that these different layers probably represent different conditions, climate conditions, relief conditions, topographic conditions, and erosional and depositional process. Because if you have layers that are richer in carbon content, maybe you has less energy in the transportation of the sediments, and or you have a climate, a past climate condition that was wetter than those layers that are poor in carbon, organic carbon, or carbon poor, okay? So we have different conditions of transportation, deposition, or formation of these materials. And it's quite important to understand how they was eroded and deposited, because it helps a lot to understand the evolution of the landscape. It's why the paleosols are so important to us, because they help us a lot to understand how the landscape evolve during time. Okay? And here I have to present some conditions, some information that's quite important to you. And the parent material, this conditionate the soil distribution in the surface of Earth. Okay, we have some works and some papers that present different soil classes according to parent material, and especially rocks, so we can understand which kind of soil class or soil group will be present in an area according the parent material, according the rock that's dominant in that area. So it helps a lot to understand which properties do you think that I have in that soil, and which kind of classes and which process could be worked or couldn't be worked in a specific soil according to the parent material. Of course, we have some exceptions, okay, but helps a lot to understand how soil was formed according to the parent material. So it's quite important to describe the parent material of soils, modern soils or paleo soils, every time. Always you can do this, okay? Of course, faults and folds, every time they favor weathering, because they are zones of weakness of the rock. So if you have some very folded, or you have a lot of faults or high density of faults in a rock, could be very easily weathered and helps the formation of soil.
Teacher, the difference between the modern soil and the paleosoil is the different conditions, or the modern soil don't have a different conditions, clim- climate difference.
Okay, Amanda, good question. We, if you remember, we discussed in the last class, we have at least 3 types of paleosols, okay?
Mm-hmm.
So we have those that are different ages from the
Mm-hmm.
modern age. We have those are formed from different conditions,
Mm-hmm.
different climate conditions, and we have those are buried, okay? So
Mm-hmm.
we can have at least these 3 types of paleosols, and is the difference from those are modern soils. Modern soils are formed in modern times from 10 thousands of years before the present, from today, okay? They need to have climate conditions that are the same from today in an area, and they can't be buried. They should be formed and present in the surface. Okay?
Okay, okay, teacher.
Okay. And so the presence and the density of faults and folds, they help a lot the weathering of the rocks, of course, and they help formation of soils, or they avoid the formation of soils, depending, of course, if folds format some different materials, okay? And faults also can expose some hard weathered materials, some materials that are hardly weathered, so maybe it also can make hard the weathering. So each case, we should understand if the parent material has faults or folds and how these materials expose easily or a hard material that could be weathered, okay? Faults also are present in areas that has a lot of pressure, and if you pressure some rocks, you also can form pegmatites and other materials that also has different resistance to weathering. So if you form pegmatite in our area that you have a lot of gneiss, these pegmatites, they present a higher resistance to weathering. So you have a lot of soils that has different conditions, different properties from those are formed from gneiss. So it's quite important to understand that some faults and folds, they could help the weathering and the soil formation, but also they can avoid the weathering and induce another soil formation process, okay? They also induce soil formation factors. They also induce the interaction between the soil formation factors, but they change the way they will be interacted. They change the road that all these soil formation factors will walk to form soil, okay? So they change how to interact and form soil, and of course, consequently, we have soils with different soil properties. On this study that was published in 2006, it's quite important because these authors, they measure the relation of different parent materials and how it influence soil properties. So if you decrease the content of silica, if you decrease the content of silicon in the parent material, you increase the content of organic carbon, you increase the pH, you increase the cationic exchange capacity, you increase the content of bases, you increase the content of phosphate, and you increase the content of clay. So it's very interesting to see if you decrease this, if you decrease in a half content of silicon, you can increase these values of these soil properties. So it's quite related, the composition of the parent material and the soil properties that was formed from that parent material, from that rock, okay? And the content of potassium and sodium decrease with increase of key minerals in the parent material. So we can estimate, we can know the content of bases, the nutrients and organic carbon, pH, and even the texture of a soil according to the parent material, according to the composition, the mineral composition of the parent material. Oh, all these studies I will share with you, okay, so don't worry, I will put on the classroom. And here we can find a table that present some of the classes of the parent materials. So we can find ultra acid rocks, we can find acid with high silica content, we can find some basic materials, oxides, organic materials, salt materials, salt-rich materials, and some examples of these rocks, of these parent materials, okay? And the silica content, the content of silicon, the content of bases, And here we can find some soil groups that are straight related to these parent materials. So if I have the parent material is oxides, it's iron-rich oxides, probably we have ferrosols or oxysoils and plantosols. Okay, if we have carbonates, maybe we have calcisoils or mollisols and another of these classes. And if you have soils that was formed from acid and rocks with high content of silicon, we probably will have arenosols. So we can see that we have a soil classification that's quite related to the parent material. Again, of course, we have a lot of exceptions because soil are not formed by only parent material, but we have several soil processes that change the properties of the parent material and form and create soils, of course. But we can see easily a relation between the soil group, the soil class, the soil properties, and the composition of parent material. Okay? Here is just an example that helps a lot to understand. This is an area in Brazil. Okay, it's the Rio Grande do Norte state in semi-arid region. And here the colors represent the type of rock. So each color represents a rock type. So this red color are granites, and this green color is limestone. This blue color represents sandstones, and this pink represent gneiss. This, I don't know which color is this. This, it's not yellow, but different kind of yellow, okay? It represents quartzites. So we can see different colors here, and if we use an image formatted by gamma spectrometry, we can see something like that. We can see easily different partners of the image, and it represents easily the parent material, the rocks that was present there. Like here, you can see here a lot of different sediments, and here we can easily see these sediments represent here. Also, we can see this highlands of quartzites. So you can see here, all these areas are highlands formed by quartzites. You can also see this yellow spot here, this yellow area, and here it's a blue area. Okay, here are sandstones. Sandstones different, very different from these ones. And here we can see very easily this area. So the chemispectrometry represents a lot the parent material composition. And why we are discussing about this, because chemispectrometry represents the composition, the chemical composition of soil, only the first 8 centimeters from the surface. So only the surface horizon, it's captured, it's analyzed by gamma spectrometry. But in this case, we can easily see that the composition of the surface horizon, the surface layer of soil, it's also highly influenced by parent material. Okay, and we can see these examples in several other areas around the earth. It's not an exception in Brazil or even in Earth. It's quite easily to identify that we have different partners in chemispectrometry that represent the differences of chemical composition in the surface horizon of the soil, but the surface horizon of the soil also represent differences of the parent material composition. We can also understand that soil, it change its composition according to the weathering and the soil formation. So we have enrichment of thorium and depletion of potassium. So some elements, they increase its contents during weathering, during the soil formation, because they are not so mobile, because they form secondary minerals, and they will be always are forming minerals in soils, and they don't be leached. And the position of some elements, some elements will be depleted during soil formation, during weathering, because they are leached. And all nutrients that you can think, like sodium, potassium, calcium, they will be leached, and they will decrease the content of these nutrients. So we can see that soil are not the same from parent material, but if I compare the composition of some materials and soil and parent material, I can understand how weathered, how leached are these soils. If I have a soil and I have the soil horizons, if I compare the chemical composition of these soil horizons, I can understand how these soil horizons are leached, are weathered, if I compare these chemical compositions with the chemical composition of the parent material. Could be very interesting to do this, because I can understand which process and the intensity of the process was acting to form this soil. Okay, the depletion of nutrients, they increase with the decrease of silicon content too. So I can understand if I have a lot of depletion of nutrients and silicon, and it helps us a lot to understand which kind of climate conditions we had to formate this soil. Depletion of nutrients and depletion of silicon, it usually occurs in wet and tropical conditions, in soils that are formed in areas of higher altitudes, higher that are above the tidal water, the sea level.
In relief, high and more plain.
Yes, yes, yes. You just need to be higher than the sea level. If you are very close to the sea level or if you are very close to the level of base, the regional level of base, you are not so depleted. You need to have freely drained conditions. You need to favor the drainage, the conductivity of water, the movement of water, so water can deplete the composition, the content of some elements. Okay. You can use the chemical composition of the soil and compare with the parent material, also to understand some specific soil process. If you compare the composition, the content of iron and zirconium and the soil horizons and in the parent material, you can understand if you have glaciation in the soil. Okay, let me show you. I forgot to use my pen today, so I can use this app just to show you how can we understand how iron and zirconium contents can help us understand some soil process. And here we have the depth 8 centimeters. And here we have the iron and zirconium content. And I can see, let me just, okay, here, and let me just change, okay. We can see in some cases, some horizons that has a lot of iron and a low content of zirconium, so could be here. And if I increase in depth, I can see a decrease of iron content. So the radio start to decrease, and I can understand that this material drops in the same radio, but the material start to increase again. And when I describe and when I identify the horizons, I see something like this in a field, and this. And this is a CR horizon, or even R rock layer. Here is an A horizon, and here it's a B horizon. As we can see here in this picture, the chemical composition of the B horizon, it's iron diplet. If I compare this chemical composition with the surface horizon and with the subsurface horizon, the parent material. So this horizon, it suffered in the past glaciation, okay? Oh, just a moment, someone asked me to enter in the class. Okay, maybe. Okay, sure, she's here. No, so let me come back here. So you can see here that B horizon, it decreases the content of iron, but keep the same content of zirconium, because zirconium, it's not so mobile. We don't lost zirconium during weathering, because zirconium, it composes hardly weathered minerals, like zircon, like quartz, like ilmenite, and several other minerals that are very resistant to weathering. So we don't lose zirconium during weathering, but we can lose iron during reducing conditions. So I can see that this soil profile, this was formed in reducing conditions that reduce the content of iron in this horizon. And it's quite easily to see that the surface horizon has a lot of oxygen, maybe because the roots or the organisms, or because the water not flooded this horizon, and the water, the tidal water, just flooded the horizon. Okay.
Teacher, the presence of the iron in horizon A can be the transport the area near this soil can be.
Yes, yes, can be. But so I have to compare the chemical composition of this horizon, the surface horizon, the A horizon, and the subsurface horizon, or the parent material. So I can say, okay, this material is an overlying material that's not the same from here, or could be the same, but just not suffered glaciation in the past. Okay.
Mhm. Okay.
Because you can think that this soil can be formed in oxidation conditions, conditions that you have a lot of oxygen, but because a change of climate or a change of relief, topography, some horizons start to suffer glaciation, and this change the composition of the B horizon. Okay?
Okay.
Okay. Everyone understand this graph, this picture? If you don't understand this and how the chemical composition help us to understand, to know that these horizons suffered glaciation in the past, please let me know, okay? It's quite important to understand that. We use zirconium because this element, it's not leached, and we use iron because iron, it's a good proxy, it's a good indicator of glaciation conditions, past glaciation conditions or modern glaciation conditions is not a problem. Is the only way that you can leach iron if iron is in a reducing condition, in a condition without or with low content of oxygen. Okay? We can see some old studies, but very good studies that present that parent material influence the soil structure. So we have different kinds of structures or type and size and grade of the structure, depending specifically from the parent material, because it dependently the iron content and how this material could be weathered and how this material could produce clay or sand contents, and these materials helps a lot to preserve or to degrade organic carbon and soil organic matter, and soil organic matter and iron and clay are very important to formation of soil structure. So we can easily see some relations between the parent material that you are describing in the field and the soil structure. This is not so helpful to paleosols because the soil structure of paleosols, they change a little bit. We will discuss this in the next class, in the next weeks, but we can saw some of these relations, okay? Some parent materials doesn't help a lot to form some types to some specific types of soil structure. So we can understand how the parent material also can help us in the description and the understanding of the formation of a paleosol, but it's not so easily, it's not so clear as we are using or studying modern soils. And now I have to make a question to you. I always love to make questions. How parent material changed from modern soil to a paleosol? Think how the parent material could change its properties between the formation of a modern soil to a paleosol. How can you see that? Is the ask is the what Amanda asked me in the beginning of the class, but now I ask you all, how can we see this change of the parent material, or how this material can be changed through time? Can anyone help me?
The question. I started the class. I think the color can be the color property is the used for explain about the modern and soil in paleosoil.
Okay, but the color of the parent material could change?
No, the color of the soil is the important to explain about the difference in modern soil and paleosoil. Okay,
Okay,
or
but
no?
uh-huh.
Okay,
No,
also the climate we can be the difference, the color between the modern soil and paleosoil is explained about the difference uh, climate. Okay.
okay. Uh-huh. But Amanda, I'm asking
Mm,
how
the
the parent
carbon.
material properties could change from a modern
Mm,
soil to a paleosoil.
mm,
Do you understand now?
yes, yes. Um, I don't speak in Portuguese, but I or English, but I think is the compost, the material compost in the parent material because I we have a material more easy weathering and we have more material parent material more difficult in it is the important for change modern and parasol I think.
Okay, so you think that the composition of the parent material could change?
Yes.
Okay, yes. How?
Mm.
Is how the is the key word in this question? How the composition of parent material could change?
um, if I have a parent material compost with more compost uh, with quartz
Okay.
example.
Okay.
Okay,
Okay.
I have material parent material more difficult for to weathering, and if I have a parent material more rich with uh, a basis for like calcium, magnesium. I have a parent material more easy to weathering. Mm, okay.
Okay. No, I understand. It's an answer that's very similar what Nedima write in the chat. She says that when the plant materials of modern soils are acted upon by factors of soil formation over a million of years, they deplete some original mineral content. So we lose some minerals because they are destroyed by weathering and leaching. Uh, you usually don't find a paleosoil with pyroxene or olivine or some minerals that very easily weathered, but you also don't find these materials in modern soils. It's quite hard to understand that some minerals that easily weathered, they will be present in modern soils too, because weathering and leaching just destroy them. So, Nedima, your answer, and Amanda, your answer are right. They all right, but you should think that the weathering, it's always destroying these easily materials, these with easily weathered materials. So it's just the content of a easily weathering mineral. It's not a good proxy to identify a paleosoil, because you can identify a lot of soils that are modern, but they don't have this easily weathering minerals. Okay, generally you can find in Brazilian soils, and I think that a lot of African soils you can find something like smectites, lights, or even you can find something like pyroxene or olivine in these materials because they are just loosened by weathering. Okay. Let us try to think how these materials, these parent materials, could be changed by time. Let me just stop because I don't want to present to you the answer. Okay, just me change. Okay, this here. And I share my screen again. Okay, just a minute. And now I will share. Okay. We'll keep in this question, how parent material could be changed by time from the formation of a modern soil to formation to a paleosoil. How parent material could be changed by time. Not only by weathering, because weathering, it's always acting even in modern soils, okay? So it's a good way to think, but it's not so right because some modern soils also are highly weathered.
Teacher, can be the relief, the important for to ocasionar these changes.
So relief could change the parent material.
No, no.
No. What?
The relief is important for to change the oh my god, 1 minute, teacher.
No problem.
No problem.
Take your time.
The presence of different parent material can be changed in the formation of the modern soil and the paleosoil, I think.
But how these materials could be changed? It's not an easy question.
Not this question.
No.
Because the different relief is different reliefs cause different materials, parent material of the different parts of the area. The transport of this parent material for this formation. I don't know more.
Oh, okay. No problem. Let's think about what define paleosoil. Remember, in the last class, we discussed about the types of paleosoils. So we discussed that a paleosoil can be buried. And the burial of a soil, it's quite important to understand how the parent material could be changed. Because if you bury a soil, you change from a modern to a paleosoil, okay? And if it are buried, what do you think that could be changed? How they can change? First of all, you can add a new material. You can add a different material
Mm-hmm.
that overlying this soil. So you can increase the chemical composition difference between the soil horizons because you're adding overlying material that has a different composition. Okay, the burial process also could influence the diagenesis of these materials. So you can decrease the bulk density, you can fulfill some faults, you can produce some materials that cement the rock or cement the parent material or fulfill the voids of soil and has a different composition. Or even the bioturbation, because the change of climate conditions also can differentiate and mix the parent material properties. Okay, so the burial process it's quite important because first of all, it's can possibly add a new material, and the overlying material has different properties. You can have overlying material composed especially from eroded sandstone, and this eroded sandstone, these sediments, they burial or they cover a soil that was formed from a basalt or a gneiss or a limestone. And of course, it's easily to think that all these layers, all these materials has different compositions. And this burial process so increase the diversity of the composition and helps a lot to understand how some process could act in the formation of this paleosoil, because these materials can be very easily leached, can be very easily wafered, or can't be easily wafered. If you have a lot of sediments that cover a paleosoil, cover a soil, I'm sorry, and these sediments, they have a high content of calcium carbonate. This calcium carbonate, the calcite, could be easily wafered if the climate conditions favor the weathering of the calcium carbonate, and the solution will be very rich in calcium carbonate content, and these materials could cement some horizons or can fulfill some voids of soil or can fulfill some faults of the parent material and change the composition of the soils, layers, and parent material. So it's quite important to understand this action, okay? And the diagenesis, it's quite important too, because the pressure of the overlying material can induce the changing of some minerals. So we can come back with the weathering. The weathering, it's also destroying primary minerals and creating secondary minerals. But that diagenesis can come back, and we can change a secondary mineral to a primary mineral in some cases. Someone asked me, let me just see. Oh, Carolina, please.
Yes, I want to know if this overlying material could be the a parent material for a new soil, or it will always be a sediment.
I'm sorry, Carolina, could you repeat, please?
My question is if this overlying material that buried a soil could could turn into a parent material, or it would always be just a sediment?
Oh, no. Could be another parent material. Can be some lava or another kind of material. Can be organic material, not even just sediments. Can be a soil that was eroded from another area and buried soil that was formed in situ. So we can have different kinds of materials that was eroded and deposited and buried this soil. Okay. Oh, welcome. It's why we can have several different chemical compositions of these materials. It's because we can see a lot of materials that can bury a soil, and this burial process is very common, especially in wet and tropical areas, because we can always see erosion, especially in South America and Africa, because we have some climate change in a recent past. So these climate change, they help a lot the erosion and the burial process of some soils. Okay. So parent material can be easily changed by the burial process, because this burial process, they can increment the diversity of chemical composition, and this could induce cementation or other process. And this burial process can induce diagenesis and the reduction of water content, the reduction of bulk density, and this help to some process like reduction. This soil can be reduced, so some oxides can't be formed in paleosols, because we have the decreasing of void content, decreasing of porosity. Okay, but we can also see the bioturbation, because the changing of climate conditions could change the stratum, the layer, the chemical composition. Okay, this is actually important when you think that we could have soils formed from sediments like these ones. The ripple marks are progressive destroyed by bioturbation through time, because we have a lot of materials that are organized in layers, and these layers, they progressive are destroying by the bioturbation, the weathering and leaching, and we hardly can find this morphology in paleosols, because time helps to destroy these marks that help us to understand, okay, easily I can understand that these horizons and these layers and all this soil was formed by alluvium or colluvium. It's not so easily to identify these materials in paleosols, because these marks are destroyed by time, destroyed by weathering, leaching, and bioturbation. We can see in these cases, it's quite easily to find that we have a material here that's very, has a gray color. It's quite easily to differentiate it from this brown and dark brown color. So we have two different materials. This one buried this material, so it increased the input a different material in the soil, and this yellow or brown yellow color are formed by the leaching and the weathering of this material, which migrates from this horizon, the subsurface horizon, from this deeper horizon. So the add of this material are increasing the difference, the diversity of minerals, morphology, color, consistency, texture of this horizon. So these burial processes are increasing a variation, diversity process in the soil formation. In the soil, it's quite easily to see also this buried sandstones, so we can see a lot of quartz grains here, some dark layers that probably are related to buried A horizons, okay? And we can see here another material that it's not so rich in quartz veins. We can see some pebbles like here. It's not so easy to find this quartz grains here. So probably this material has a different composition from these ones. So I buried all this material and I have a different composition from here to here. So this modern soil that's forming and buried this soil has different compositions and different properties. Here it's quite easy to see again this material, this burying a material that has a different texture, color. Here we can see a lot of pebbles and grains that are some rounded materials, not so rounded materials. And here we have a finer texture, probably fine sand or even silt texture. And here we have a lot of different materials, coarse materials that probably are related to more rapid deposition, and here calm and finer deposition. And the burial process also induce some process that are the loss of water. So we can see in this case the formation of modern soils that are rich in smectite, and smectite has a lot of water in the unit cells. And when this material is buried, we reduce the content of water. So we lost water from this situation to this situation, okay? And we also can lose the voids. We can increase the bulk density from this option, from this case to this case. So we can increase the bulk density, reducing voids, reducing the porosity of soil and the parent material. And here we also can lose water, and consequently we can change the minerals that we can find in the parent material and the minerals that we can find in soil. It's called smectite ylitization. It's formation of ylite from smectite because you lost water. Okay, so diagenesis change the porosity and change the minerals that we can find. Why porosity is important, why the size and connection between voids are important to soil. Well, we can identify a lot of processes that depends on the void connectivity and void size, because we can find some oxides in soil because the adding of oxygen in soil, in the atmosphere of soil, because we found voids. So if we lost the volumes, if we increase the bulk density, if we lost voids, the oxides are not forming anymore, and maybe we can lose them. So when we have a soil, a paleosoil that suffer diagenesis, we can't find any more oxides or these oxides are not formed after the compactation, after the diagenesis, because we don't have voids, we don't have large voids, we don't have oxidation conditions. Someone?
Professor, and sorry, the burial, it favors this process.
Yes, yes,
Volume
yes.
loss, porosity.
Yes. To lose water and to lose voids, to decrease the porosity, you need to be a buried soil. These conditions are not formed in surface. Okay.
Okay, thanks.
Mhm. Here are some pictures that help us to see this process. Okay, so we can see here some decrease of bulk density because the material, the voids are fulfilled by cements or from some materials. In this case is calcium carbonate, in this case is silicon. And here are just the decreasing of bulk density because you pressure the material. So you don't fulfill the voids, you just pressure the material and the bulk density decrease. And here we fulfill the material, the voids, by leaching of some water with a high content of some ions or elements. Oh, I'm sorry. Here we can find some of these materials that are related from the weathering of a buried layer that now is exposed in surface. So we have a paleosol that was formed in the past in a surface condition. After that was buried, and today it's exposed. Oh, you can see the complexity of this material. It was formed in surface, after that was buried, and now it's exposed. So the calcite cement that fulfill some voids now are being losing by leaching. So we can see this color, this reddish color, is the calcite cement that's been losing some voids here that represent some material, some voids that represent the loss of this calcite cement, okay, this fulfilling material, these filling materials. But we can see that this horizon was buried in the past because we have this type of contact between coarse fraction. We can see this saturated contact between grain materials, the coarse materials. This kind of contact between grains, it evidenced that this material was buried and pressured in the past by a diagenesis condition, by a diagenesis process. So I can see by this kind of contact between coarse grains that this material was pressured in the past. Okay, pressure and filled by some materials like calcite in this case. Okay, if you already see some photos by micromorphology, if you are used to see some pictures of micromorphology, you can easily think that this material are not natural or not so common in modern soils, because in modern soils we don't see this kind of contact between coarse fraction. Coarse fraction usually are not so close. The coarse fraction, the coarse grains are not so close, and they are not in contact between the walls. They generally are just spread in an area and have punctual contact are not so face-to-face contact between the coarse fraction. So modern soils, they don't have this kind of contact, a face-to-face, a saturated contact. They are just a point-to-point contact because modern soils are not so pressured, are not so compacted, okay? Here it's quite easy to find. It's another micromorphology photo picture, and here we can see a quartzite that was pressured, and we can see all quartz grains, all these coarse grains, they are face-to-face organized. This contact are face-to-face every time. Something that we can see in modern soils, okay, or soils that are not buried, or soils are not compacted, pressured in the past, okay? And how can we measure these changes of parent material progress? First of all, the micromorphology. The micromorphology can help us a lot, like in these pictures. We can see the organization, orientation, and distribution of materials, the coarse and the fine particles in the soil. So it helps a lot. We will discuss about this in the next classes. The geochemical composition of the parent material, the soil layers, the soil horizons help us a lot to understand how these materials could be changed by time. And of course, the identification of the minerals in the parent material and the fine fraction and the coarse fraction of soils. They help us a lot to understand how these materials could be changed through time, okay? All these techniques, all these maths, we will discuss in the next class. So don't worry if you don't know how to describe or study a soil by micromorphology maths. Don't worry, we'll discuss this in the next classes, okay? It's just to understand that we need to know and we need to have a lot of tools to describe some of this process through time that change soil through time, okay? Okay, has anyone a question? Has anyone questions?
No, teacher.
No, Amanda?
No.
Carolina? Okay. Millie? Dima? Everything's okay?
Yeah.
Okay,
Everything is okay.
Oh, okay, good to know, good to know. I'm stopping the class now, okay? I will share more material, more references to you all, and I ask that you read the material. So in the next class, we will discuss how the organisms, the plants, and the animals change soil and how we can measure these changes through time. How can we measure vegetation and animals can change the powder source, okay?
Okay, teacher.
So, see you. I hope that you are well. Bye-bye.
Bye-bye, teacher. Bye, guys.
Bye-bye.
Thanks, bye.
Bye. Thanks, teacher.
See you.